Hello my dear students, welcome to my YouTube channel that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the sp3d2 hybridization, and for this concept I am taking the example of sulfur hexafluoride. So today's example is sulfur hexafluoride. The molecular formula for sulfur hexafluoride is SF6. Before starting the hybridization, let's make the Lewis structure of SF6 first. Here I am taking sulfur, here I am taking fluorine, the second fluorine, the third fluorine, the fourth fluorine, the fifth fluorine, and the sixth fluorine. Now, let's talk about sulfur first. The atomic number of sulfur is 16. So its configuration will be 2, 8, 6. So that means sulfur is having 6 valence electrons. So let's mark 6 electrons around sulfur in the Lewis structure. The first electron, second, third, fourth, fifth, and the sixth. Now, let's talk about the fluorine. The atomic number of fluorine is 9. So the configuration will be 2, 7. That means fluorine is having 7 electrons in its valence shell. So let's mark 7 electrons around all the fluorine atoms in the Lewis structure. So let's come to the first fluorine. That's the first electron, second, third, fourth, fifth, sixth, and the seventh. Let's come to the second fluorine. The first electron, second, third, fourth, fifth, sixth, and the seventh. Now that's the third fluorine. First electron, the second, third, fourth, fifth, sixth, and the seventh. Now let's come to the fourth fluorine. The first electron, second, third, fourth, fifth, sixth, and the seventh. Now let's come to the fifth fluorine. The first electron, second, third, fourth, fifth, sixth, and the seventh. Now let's come to the sixth fluorine. The first electron, second, third, fourth, fifth, sixth, and the seventh. Now, what's going to happen? All the fluorine atoms are going to make 1-1 bond with the 6 valence electrons of the sulfur. So, that's the bond of first fluorine with sulfur. Now, that's the second bond of second fluorine with sulfur. Now, it's the third bond of third fluorine with sulfur. Now, it's the bond of fourth fluorine with the sulfur. Now that's the fifth bond of fifth fluorine with sulfur, and that's the sixth bond of sixth fluorine with the sulfur. Now let's count the number of valence electron for all the fluorine after making 1-1 bond with sulfur. Let's start with the first fluorine. That's the first electron, second, third, fourth, fifth, sixth, seventh, and the 8th. So fluorine has attained 8 electrons, that is octet, after the formation of 1 bond with sulfur. Now let's count the number of valence electron for the second fluorine after the formation of 1 bond. That's the first electron, second, third, fourth, fifth, sixth, seventh, and the 8th. So second fluorine has also attained octet. Now let's come to the third fluorine. That's the first electron, second, third, fourth, fifth, sixth, seventh, and the 8th. So that means third fluorine has also attained octet, that is 8 electrons after the formation of 1 bond with sulfur. Now let's count the number of valence electron for the fourth fluorine. The first electron, second, third, fourth, fifth, sixth, seventh, and the 8th. So again The fourth fluorine has also attained octet after the formation of one bond with sulfur. Now, let's count the number of valence electron for the fifth fluorine. That's the first, second, third, fourth, fifth, sixth, seventh, and the eighth. So the fifth fluorine has also attained octet after the formation of one bond with sulfur. Now let's come to the last, sixth fluorine. That's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. So the sixth fluorine has also attained octet after the formation of one bond with sulfur. Now, let's count the number of valence electron of sulfur after the formation of 1,1 bond with 6 fluorine atoms. So that's the first electron, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, and the 12th. So that means sulfur has attained 12 electrons in its valence shell, which are more than 8 after the formation of 1,1 bond with 6 fluorine atoms. Why sulfur is capable of expanding its octet, that is having more than 8 electrons in its valence shell? Because sulfur is available with vacant 3d orbitals, which we are going to do in the hybridization. Now, let's talk about the hybridization now. Here in SF6, we are having central atom. We are having central atom to be sulfur, because sulfur is forming maximum number of bonds, that is 6 bonds. Now, what will be the electronic configuration of sulfur? The atomic number of sulfur is 16. The electronic configuration in terms of subshells and orbitals. The valence shell electronic configuration will be 3s2, 3p4. So that means, firstly, let's draw the orbital diagram. The s subshell is having one orbital, so that's the one orbital of 3s. Now the p subshell will have 3 degenerate orbitals, the orbitals which are having equal energies. So that's the 3p. Now in sulfur we are having 3s, 3p, and also the 3d subshell with 0 electrons, that is vacant 3d subshell. In 3d subshell we are having 5 degenerate orbitals. Degenerate stands for the orbitals with equal energies. So in 3d we are having 5 degenerate orbitals. Now let's fill the electrons according to the electronic configuration in the orbitals. The 3s is having 2 electrons, so that's the first electron with a spin of +1/2, and that's the second electron with a spin of -1/2. Now let's come to the 3p. We have to fill 4 electrons in 3p according to the Hund's rule, and Hund's rule states that in case of degenerate orbitals, firstly all the orbitals will get 1 electron each. After that pairing will start. So in 3p we are having 3 degenerate orbitals, so let's fill the 4 electrons over there. That's the first electron, second electron, and the third electron. So now here the degenerate orbitals have got 1 electron each. Now the pairing will start from the 4th electron. So that's the 4th electron with the spin of -1/2. Here we are available with only 4 electrons in 3p, so we have to stop it over here only, because we have filled the 4 electrons in 3p. So that's the ground state. That's our ground state. Now let's come to the Lewis structure. In Lewis structure we can easily see that sulfur is forming total of 6 covalent bonds. Now all the bonds between the sulfur and fluorine are the single bonds. So whenever there is a single bonds, they are all sigma bonds. That means sulfur is forming total of 6 sigma bonds, and hybrid orbitals only form the sigma bonds. Now if sulfur is forming the 6 sigma bonds, then sulfur must have 6 atomic orbitals containing 1 electron each, so that they can overlap with the atomic orbitals of fluorine containing 1 electron for the formation of the covalent bond. So for the availability of the 6 orbitals containing 1 electron, the electron from the 3p and the 3s will excite to the 3d subshell. So the electron from 3p which got paired up will excite from 3p to the 3d orbital, and electron from 3s will excite from 3s to the 3d orbital. So let's make the excited state. That's our 3s. These are the 3 degenerate orbitals of 3p, and these are the 5 degenerate orbitals of 3d. Now in 3s initially we were having the 2 electrons, now we are left with only 1 electron. In 3p initially we were having the 4 electrons, now we are left with only 3 electrons. Now in 3d we were having no electrons, but now we are having 2 electrons in 3d. The one from 3p has excited to the 3d, and one electron from 3s has excited to the 3d. So that's our excited state. Now, as all the 6 bond in the Lewis structure are the sigma bond, so during the intermixing of the atomic orbitals, all the orbitals containing 1 electron each will be involved. So in this case, the intermixing of atomic orbitals, that's 1 from the s orbital, the 3 from the p orbital, and the 2 from the d orbitals will intermix. So here 1 s orbital, 3 p orbitals, and 2 d orbitals will intermix. They will intermix. The intermixing of atomic orbitals is called hybridization. Is called hybridization. After that, now here we have mixed total of 6 orbitals, 1 from s, 3 from p, and 2 from d. So we have mixed total of 6 orbitals. So we are going to have 6 new hybrid orbitals, 6 new hybrid orbitals of equal energies. That means the new 6 hybrid orbitals will be degenerate orbitals, that is with equal energies. So let's make the 6 degenerate orbitals over here. So we got these 6 new hybrid orbitals. The name of these hybrid orbitals will be, as this orbital has been formed by intermixing of 1s, 3p, and a 2d. So the name of hybrid orbitals will be sp3d2 hybrid orbitals. Second one is also sp3d2. Third one is also sp3d2. Fourth one is also sp3d2. Fifth one is also sp3d2, and the sixth one is also sp3d2 hybrid orbitals. So we got total of 6 hybrid orbitals which are named as sp3d2 hybrid orbitals. Now we are going to have 16.66% s character, 50% p character, and 33.32% d character per hybrid orbital. That's why they are named as sp3d2 hybrid orbitals. Now, in the parent orbitals, the orbitals of 3s, the 3 orbitals from 3p, and the 2 orbitals of 2d, we are having total of 6 electrons. The first electron, second, third, fourth, fifth, sixth. So we have to redistribute these 6 electrons in the hybrid orbitals. So let's do that according to the Hund's rule. The first electron, second, third, fourth, fifth, and the sixth. Now let's talk about the fluorine now. The fluorine. What's the atomic number of fluorine? That's 9. So the configuration will be 2s2, 2p, 5. Let's make the 2p orbital of fluorine. So that's the 2p. Now in 2p we are having 5 electrons. That's the first electron, second, third, fourth, and the fifth. Now let's come over here. I'm making the 2p of first fluorine. That's the 2p of first fluorine atom. And it's having 5 electrons. The first, second, third, fourth, fifth. Here one orbital is left which is having 1 electron, and that's going to have head-on overlap with the sp3d2 hybrid orbital of sulfur for the formation of sigma bond. So sigma bond will be sigma sp3d2p, because this sigma bond has been formed by head-on overlap of sp3d2 hybrid orbital of sulfur with the p orbital of fluorine. Now let's come to the second fluorine. That's the 2p of second fluorine atom. In this again we are having 5 electrons, 1, 2, 3, 4 and the 5. Here also we are left with one orbital which is having 1 electron, and this is going to have head-on overlap with the hybrid orbital of sulfur. So this will be again sigma sp3d2p, because this sigma bond has been formed by head-on overlap of sp3d2 hybrid orbital of sulfur with the p orbital of fluorine. Let's come to the third fluorine. That's the 2p of third fluorine. Again this is having 5 electrons. So the first electron, second electron, third electron, fourth electron and fifth electron. And here again we are left with one atomic orbital which is having 1 electron, which is going to have head-on overlap with the sp3d2 hybrid orbital of the sulfur for the formation of sigma bond. So that's again sigma sp3d2p. Now let's come to the fourth fluorine. That's the 2p of fourth fluorine. Again this is having 5 electrons, 1, 2, 3, 4 and 5. Now here also one atomic orbital is left which is having 1 electron, and this is going to have head-on overlap with the sp3d2 hybrid orbital of sulfur for the formation of sigma bond. So again this is sigma sp3d2p. Now let's come to the fifth fluorine. That's the 2p of fifth fluorine. Again this is having 5 electrons, 1, 2, 3, 4 and 5. Now here again we are having one atomic orbital which is having 1 electron, which is going to have head-on overlap with the sp3d2 hybrid orbital of sulfur for the formation of sigma bond. That's again sigma bond, sigma sp3d2p. Why so? Because this sigma bond has been found by head-on overlap of sp3d2 hybrid orbital of sulfur with the p orbital of fluorine. Now let's come to the sixth fluorine, the last one. That's the 2p of sixth fluorine. Again, this is having 5 electrons. That's 1, 2, 3, 4 and the 5. Here also we are left with one atomic orbital which is having one electron, which is going to have head-on overlapping with the hybrid orbital sp3d2 hybrid orbital of sulfur for the formation of sigma bond. So this sigma bond is also sigma sp3d2p, because this sigma bond has been formed by head-on overlap of sp3d2 hybrid orbital of sulfur with the p orbital of fluorine. So that's all about the hybridization. Now let's talk about the structure. We got the hybridization to be sp3d2. The standard structure for sp3d2 hybridization is octahedral. The another name for octahedral is square bipyramidal. It's square bipyramidal. Now the structure is like, that's the sulfur, the first sigma bond with first fluorine, second sigma bond with second fluorine, third sigma bond with third fluorine, fourth sigma bond with fourth fluorine. Now I'm just imaginarily linking the fluorine atoms to make you understand this structure in 3 dimensions. This is the square equatorial plate. Now we are left with 2 fluorine. We got the 5th fluorine over here and the 6th fluorine over here. Now just imagine this structure in 3 dimensions. All the bond angles are 90 degree, and this bond angle, imagine it in 3 dimensions, this bond angle is also 90 degrees. So this structure is called octahedral, and all the sigma bonds over here are sigma sp3d2p, because this sigma bond has been formed by head-on overlap of sp3d2 hybrid orbital of sulfur with the p orbital of fluorine. Now that's all about the hybridization. At last, let's come to the energy points. Here 2 types of energies are consumed, or there are total of 2 endothermic processes. So I'm writing them. First one is consumption of promotional energy. That is, energy is required to promote electrons from 3s and 3p to the 3d orbitals. For that, energy is required, so here is the consumption of promotional energy. Another type of energy consumed is the energy required for intermixing of atomic orbitals. So here is a consumption of hybridization energy, the energy required for intermixing of atomic orbitals. After that, when the 6 sigma bonds are formed, the energy is released. So I am writing the energy is released during the formation of 6 sigma bonds. During the formation of 6 sigma bonds, which compensates promotional energy and hybridization energy. as both of the endothermic energies, that's the promotional energy and hybridization energy, is compensated during the formation of 6 new sigma bonds. That's why the formation of sulfur hexafluoride SF6 is chemically feasible or practically possible. So that's all about the hybridization of SF6 or sp3d2 hybridization. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.